Here's the second part of paper 3, AQA A-level chemistry, multiple choice section. Okay, right. Number 5, which can both be empirical and molecular formula of a stable compound? Okay, so of course the empirical is the simplest, simplest ratio. So straight away we can rule out that one because that's not the simplest ratio, is it? So get rid of that. CH3, well, carbon likes to form 4 bonds, so that's not going to be a stable compound for the molecular formula. Of course, you could have C2H6 for empirical formula, but there's no molecular formula. It can be CH3. Likewise, nitrogen forms 3 bonds, not 2, so that's not right. So it must be that one. And just to show you, you can have carbons forming 4 bonds there in methanol, and you can have lots of things like of that. So C4H8O2 would be butanoic acid and so on. So that is the answer there. Number 6, diagram shows the correct bonding and correct polarity of oxygen difluoride. Okay, there are no dated bonds, so forget that one and that one. Now, fluorine is more electronegative than oxygen, so there's going to be the partial negative charge on the fluorines, positive on the oxygen. That's the one there. Okay, so here's about the Rutherford experiment, GCSE really, so but here it is anyway. Right, so they're firing helium nuclei, alpha particles against a thin sheet of gold, and most of them are detected at P. What conclusions can be drawn from the detection at point P? Well, that one isn't, that's wrong. They didn't tell them that. They didn't even know what protons were then. They didn't know what neutrons were either. Gold atoms are mainly empty space. That's the right answer, because that's why the alpha particles can go straight through. Right, next question. When they were fired, about 1 in 8,000 of the particles were detected at Q, so that means the particles are bouncing back. What made the alpha particles bounce back is because you've got positive charge in the gold nucleus. And that was showed them they had a it's only a very small number, very highly positively charged small nucleus. So which is the best one there? Is A. Okay, that is the best one there. Nine, which reaction represents the termination step? Talking about free radical reaction. Well, you need 2 free radicals coming together, don't you, for a termination step? Like you need Cl and a dot there and Cl with a dot there. They come together and they form a non-free radical. That's why. So you get rid of the free radicals. So you want one with 2 free radicals, and the only one with 2 free radicals reacting is D. The others have only got 1 free radical in there. Okay, which statement is correct about the molecule shown? So we've got not a benzene ring, we've got an aldehyde group and so on. Which is correct? It reacts with HBr in electrophilics, not electrophilic, it's an electrophilic addition, that would be, wouldn't it? That's wrong. Right, it reacts with NaBH4 in a nucleophilic, right, it will react with that, H minus from the nuclear, but it's not nucleophilic addition elimination, it's just nucleophilic addition, it's not that. It won't react with KOH in an elimination reaction. The reason being is because you remove, in an elimination reaction, you remove the bromine and a hydrogen from the carbon next door. Well, if you look at those 2 carbons there, they don't have a hydrogen attached, so you can't eliminate that molecule. KCN in a nucleophilic substitution reaction, that will work. Okay, CN minus from the KCN. Right, you've got a delta positive on that carbon there, do it in green. So you're going to get that going there. So D is the right answer there. That's quite a lot of thinking in that question. Right, 11. Right, which statement is better? Is about these two alcohols. Now, the best thing to do is just quickly sketch them out. So we've got 2-methyl butanol, like that. So that's a primary alcohol. But this one here, if you draw it out, it's not immediately apparent looking at the name. If you draw it out, you'll see that that is actually a tertiary alcohol, which will make things right. So they can both, yeah, you can form esters from both of them, so you can hydrolyze the esters. That's right. Can you oxidize them both? You can't, can you? Because this is a tertiary alcohol. You cannot oxidize that with acidified potassium dichromate. Both give you 4 peaks in the NMR in the 13C spectra. That's wrong. They both give you 5 peaks. Yeah, you've got 5 separate carbons, and each one's in a different environment in both of those molecules, and formed by the hydration of 2-methyl butene. No, you can't do that. So let's move. So the answer is A. Right. Right. This one here about reaction orders is a bit bigger. Now, W and X react in the presence of a soluble catalyst Y. When the 4 concentration of W and X and Y are all doubled, the rate increases by a factor of 4. First of all, you might think, the catalysts can appear in rate equations. There's quite a lot of rate equations you probably come across where H plus appears in the rate equation, but it's not actually a reactant, and that's because it's a catalyst. So don't think that you can't have Y in the rate equation. You can, okay, even though it's a catalyst. What you can't have in the rate equation, of course, is Z. And there's a couple there, there's one there with Z in, so we'll get rid of that straight away. Okay, now if you double the concentrations of the reaction, the rate increases by a factor of 4. Well, if you doubled that, well, the W would make it go up by a factor of 4, and the X would make, so that would go up by a factor of 8, so it's not that one. You'd have a similar thing there with B, go up by a factor of 8. This one, doubling X would double the rate, and doubling Y would double it. So you get 2 times 2 times 2 is equal to times 4. So that's the answer there. Question 13. Right. So you want to find out the rate order with respect to X. Right. Now, and you're only changing X. And you wanted to show that rate is equal to X squared. So that means the curve, you put rate there and concentration of X, it will be like that, won't it? It will be a curve. It won't be the blue, it won't be, it's not blue, it won't be the straight line like that. So the answer is D. That's the right answer there. Okay, so this is represents the process with the standard enthalpy atomization of iodine. So this is where you have to know the definition. Okay, it's so standard enthalpy of atomization is when you form 1 mole gaseous atoms from element in its standard state. Okay, so we can see that that one is wrong and that one is wrong, whatever, because you're forming 2 moles. So forget about them. So which one is right? Well, it's this one, because iodine, the standard state of iodine is a solid. So A is the correct answer there. Okay, what structure is formed by aspartic acid in solution at pH 12? Right, pH 12 means you're going to, any carboxylic acid group, pretty alkaline, you're going to will have removed that proton. So that's going to be minus. And any amino group is not going to be protonated at pH 12. It's pretty alkaline. You will lose that proton, so it'll be NH2. So you can see the only one which is right there is D, where you have a deprotonated carboxylic acid, and an NH2 group. Right, how many peaks are there in the 13C spectrum of 1,4-dimethylbenzene? I think I'll make that a bit bigger. Okay, right, so let's draw it out. 1,4-dimethyl, so there's a methyl on number 1, 2, 3, 4, methyl there. Right, so these two are going to be the same, those carbons, yeah. These two carbons are in the same environment, and if you look, those 4, they're all in the same environment. So you'd get 3 peaks would be the right answer. Which of these period 3 elements has the highest melting point? Right, now it's not going to be phosphorus because that's a simple molecule. It's not going to be sulfur, that's another simple molecule. It's going to be aluminium or sodium, they're both metals. And the answer is aluminium has got the highest melting point. Oh, elements, yeah. Aluminium's got the highest melting point because you've got an Al3 plus ion, whereas sodium has got a much bigger Na1 plus. So the attraction of the delocalized electrons, which is what's holding the metal together, is much bigger with the aluminium ion than with the sodium ion. So A is the right answer there. Okay, this one here. Chlorine reacts with dilute cold aqueous sodium hydroxide. Right. What are we going to get there? Right, let's write the equation down. So chlorine reacts with NaOH. So this is group 7. You need to know this. Sorry. The disproportionation reaction, you get sodium chlorate 1, you get sodium chloride, and you'll get H2O. So the oxidation number of chlorine there is 0, plus 1 there, minus 1 there, disproportionates. So sodium chloride 1, and water is the right answer. And that's sodium chlorate 1, that stuff, because the oxidation number of chlorine is there is 1. It's not sodium chlorate 5. Okay. 19. Right, this is right. Which products are formed when magnesium reacts with steam? It's straightforward factual recall, really. Magnesium doesn't react like the other group 2 elements. Don't react with cold water, but it will react with steam, and it won't give you the hydroxide, it will give you the oxide and hydrogen gas. So magnesium oxide and hydrogen is the right answer. Okay, 20. Which observation would confirm that ammonia gas is released? And the reaction is neither here nor there. We don't need to know about that reaction. We're just testing for NH3 gas, right? That will dissolve in water to form an alkaline solution. So if you have damp red litmus, it will turn it blue. Now, so damp red litmus paper turns blue. You shouldn't touch the solid. No. You just wave it about in the gas above. When it's held, damp red litmus turns blue and held just above the solid. Okay. If you touch the solid calcium hydroxide, because that is alkaline, that's slightly soluble, and it will give a strong. It will turn blue. It won't show you that you've made ammonia gas, though. It will just mean that you've got an alkaline in the you've got something in the solid which dissolves to give an alkaline solution. Okay, the repeating unit of a polymer. Let's make this bigger. Right. Now, if we look here, so that's the repeating unit of the polymer. Right, this is a bit of a red herring in the middle here. This isn't. That's they're showing a repeating unit. That is that you've got an amide link, but that's already in there. All right, which pair of monomers? Actually, it's not a red herring. You can actually see what you've made it from a dicarboxylic acid there, and so that's the dicarboxylic acid, and this is the diamine. Okay, and it's actually nylon 6,6. That's what it is, isn't it? So the dicarboxylic acid, well, you can have a dicarboxylic acid or you can have a diacyl chloride. To make that, and that's going to react with the NH2 group on the amine. So, and you're going to lose HCl there to form an amide linkage. That's what's happening. So what we're looking for there is right, that wouldn't work because it's just a dicarboxylic acid. That would work. Yeah. Which monomer or pair of monomers? Sorry, that wouldn't work. That would work. Yeah, this one wouldn't work because you've got 6. You've got 6 carbons there, and there's only 4 there, so that wouldn't work. That's what was throwing me a little bit there. So C is the right answer. Okay. A wouldn't work either. It would polymerize, but it wouldn't, because that acyl chloride would react with the NH2 and an adjacent one, but it wouldn't give you that that polymer. It would be a different polymer. Okay, right. So make us right. This is the structure of a polyester chain. Okay. And it's all about intermolecular forces and stuff. Right. This plastics only soften at high temperatures. Okay. Right. Hydrogen bonds. Well, you can't get hydrogen bonds between polyester chains, can you? Because you haven't got any hydrogens. You need a hydrogen attached to O, N, or F. And you haven't got that. But you could get dipole-dipole interactions between the chains. That's going to be delta positive. That's going to be delta minus. And you could also get van der Waals forces, of course. So that one's wrong. Permanent dipole-dipole forces and van der Waals forces exist. That's correct. B is correct. Just to show you, C and D are not correct. Right. The carbon bonds in the chain are strong, yeah, but when you melt it, you're not breaking those. You're not actually breaking any covalent bonds. You're just breaking intermolecular forces. So that's wrong. And D is also wrong because D says, I think, about oxygen. The carbon-oxygen bonds are strong. They are strong, but they're not broken when you melt it. So that's neither here nor there, whether they're strong or whatever. Right. Now, right, we've got nitration of benzene, mixture of concentrated nitric and sulfuric acid. Right, which statement is correct? You can see here what's happening. The nitric acid is going to pick up picks up a proton to form H2NO3 plus, which then falls apart into the NO2. So the nitric acid is acting as a base. It's reacting. It's not a catalyst. It's not an electrophile. It's not a reducing agent because the oxidation number of nitrogen remains the same throughout. It's +5 in both of those, so there's no redox going on there. It's an acid-base reaction, and the nitric acid is behaving as a base, and the sulfuric acid is behaving as an acid. So A is the right answer there. Okay, this is about base strengths then, I think. Let's have a look at this. Right. So, aqueous solutions of ammonia, ethylamine, and phenylamine are prepared. Each solution has the same concentration. Okay, so we don't have to worry about the solubility. We just need to worry about the base strength. Right, so if you remember, phenylamine is very weak base. The reason because the lone pair on the nitrogen is delocalized on the electron on the benzene ring, so it's not available for accepting protons. Ethylamine is a better base than ammonia because remember, alkyl groups have a slight tendency to push electrons away from them into the nitrogen, so that makes the intensity of the lone pair a little bit stronger. So this is the strongest base. Okay, so that's going to give the right. So which is going to give the lowest pH is going to be the phenylamine, because it's going to be closer to 7. So we haven't got that. Right, so I think we're going to have to, it must be the highest to lowest first. Well, the highest pH is going to be the ethylamine, because it is the most basic. And then it's going to be the ammonia. That's going to be next, medium. And this is going to be the lowest pH. So it doesn't say, I would have thought it would be ascending order, but C is the only possible one. You can have that as descending order, going from from the highest pH to the lowest pH. But that's the only possible alternative there. Okay. Next one. Which element forms an ionic oxide which reacts with strong alkalis? Right, now ionic oxides, which ones form ionic oxides? So it's all of these three, because they're all metals. Magnesium and sodium oxide are basic oxides. They won't react with strong alkalis. Aluminium oxide will. It's amphoteric. So that is the answer there. And sulfur oxide, of course, is covalent, SO2 or SO3. Right. Right. We've got a ligand exchange reaction with, with a bidentate ligand here. So bidentate ligand. Right. A, the coordination of cobalt decreases. It doesn't. You've got 6. Coordination is the number of covalent data covalent bonds forming to that. You've got 6 in that one. You've got 6 in that complex. So that's not right. The enthalpy change is large and positive. That's wrong, because delta H doesn't change much there, because you're forming 6 bonds and you break 6 bonds. So it's about 0. Entropy is large and positive. This is correct, because if you look with these bidentate ligands, you end up with more species on the right than the left. On the left, you've got 4 species. You've got 1 of them and 3 of them. On the right-hand side, you have got 7 aqueous species. So that means the disorder is, so delta S is positive, that one there. The shape of the complex changes it doesn't. It remains octahedral throughout, because it's got 6. It's forming 6 bonds there. Okay. This 27 is a straightforward, you've got to know this one really, you can't really work it out. When you have a bidentate ligand, or a bidentate ligand, then there's a possibility of 2 optical isomers. So this is no bidentate ligands except in that one. So that is the correct answer, because if you have cobalt, let's see, right, these are, right, I'll draw the ligand as, I'll just draw it as the bidentate ligand like that. Right, so you're going to have 1 there, and have 1 there, and you can have 1 there. If you imagine a mirror here, the mirror image of that, you can't superimpose it on that. So it exists as 2 optical isomers on non-superimposable mirror images. You've really got to just know that one, really. Okay. 28. Right, this one is tricky. How many structural isomers C5H10O react with toluenes? Okay, so first of all, look at the carbon-hydrogen ratio there. It's CnH2n, so we've only got 1 double bond. We don't have to worry about carbon-carbon double bonds. We've just got the 1 in the aldehyde group. So how can we do that? Right, so we could have 5 in a row. That's 1. We could have 4 in a row with a methyl. So you could have the methyl there, position 1, that position, or you could have it there as well. So you're going to get, so we've got 1 like that, we've got 2 of those with the branch, 4 with a branch, and then we could have 3 carbons with a double branch on it. So put that there. Now we couldn't have that because, could we have it? Yeah, we could. That carbon is only forming 4 bonds, yeah. So we could, there's 1 isomer like that. So the answer is there are 4 aldehydes. Of course, they're the ones that react with Tollens reagent. There's only 4 possibilities there. Okay, you can't have a cyclic or anything like that because then you wouldn't have the, you've got to have that CnH2n ratio there. Okay, 4 is the answer. Okay, this is a tricky question, I think. So let's have a look at this one. All right, make it a bit bigger. Right, this is about homogeneous catalyst, sorry. Right, we should be familiar with this reaction between the iodide and the peroxide of sulfate ion. It's catalyzed by, actually we shouldn't know that it's catalyzed by Fe2 plus and Fe3 plus. And what's got to happen is, right, the peroxide ion, okay, that oxidizes the M2 plus ion to M3 plus. I'm not balancing this, and you'll also get SO42 minus. And then the M3 plus then reacts, that actually oxidizes the iodine to iodine. Again, I'm not balancing the equation. Right, so what we want is, we've got to check that the M2 plus ion can react with the peroxide of sulfate. Okay, so remember, the most positive ones, they're always going to go forwards because they are best at taking in electrons. So, okay, that's going to be S2, that's the strongest oxidizing agent there, S in that chart there. Now, which 2 plus ions can that oxidize? Well, it can oxidize iron 2, as we know, but it can also oxidize cobalt 2 because, you know, it's more positive than that, right? So, so far, iron or cobalt could work. Let's see, will the can it oxidize? Can that oxidize? And it can oxidize chromium as well. So we haven't ruled anything out there. And can it oxidize? Well, the iodide ions. So all 3 metals are okay to react with the peroxidate. But now we need to check which of the M3 plus ions can react with the iodide ions. So this should tell us what's going on here. Right, so we need to be able to oxidize iodide to iodine. Okay, so that means, can chromium 3 plus oxidize iodide? It can't. Okay. Let me think, sorry. Right, so let's concentrate on the iodide. So we want iodide to go backwards. Okay, so that means we need the 3 plus ion has got to be above the iodine. So cobalt 3 plus and iron 3 plus should both be able to do it, to oxidize iodine to iodine. So cobalt and iron can both do it, but the one that can't do it is the chromium. So chromium cannot manage it. All the other ions, they can work, they can do it. And the reason why chromium can't do it is because the Cr3 plus is not a strong enough oxidizing agent to oxidize the iodide ions, whereas Fe3 plus and cobalt 3 plus are strong enough. Okay, so but shape, which can be influenced by the presence of one or more lone pairs. Sorry. Where is that? All right. Now, aluminium is in group 3. So it's only got 3 electrons on its shell. They're all involved in bonding pairs, so it's not that one. Right. Chlorine, well, that is definitely influenced by a lone pair. So we just draw, there's chlorine. Okay. Chlorine's in group 7. I'm going to put a dot and a cross here. Right. Chlorine is in group 7. I've only drawn 3 of its 7 electrons. So chlorine is going to have 2 lone pairs there. So they will influence the shape of the molecule. Okay. Just to show you the other 2 can't do it. Right. So phosphorus is in group 5. Right, so look at the phosphorus. Phosphorus is in group 5, so you're going to get 1, 2, 3, 4, 5. You're going to get normal covalent bonds between those. There's the phosphorus. These are all chlorines. Yeah. Right, and because it's Cl6, so then you've got a chloride ion comes and forms a dated bond there. There's a chloride ion. So you can see there's 6 bonding pairs, no lone pairs there, so it's not that one. IF6, have a quick look at that. Well, right, IF6 plus. Good, right, so we've got iodine. I've got 6 fluorines. Putting a dot and a cross in each of those. Here's our iodine. Iodine is in the group 7, of course. But we're talking, this has got a positive charge in it, so it hasn't got 7 electrons, it's missing 1, it's only got 6. And you can see I've already used 6 of the iodine's electrons up, so there are 6 bonding pairs and no lone pairs. So B is the answer. Okay. Getting towards the end of this paper. Right. This is a tricky one as well. Right. Right. So you are going to mix up these solutions, equal volumes, same concentrations, which would give the greatest mass of the solid. So let's see which. So this one is going to give us barium. Actually, that is going to give us, there'll be no reaction there. Okay. Oh yeah, there would be, because you're going to get barium, you get barium chloride, and the magnesium is going to precipitate out. Okay, so that's going to give you the solid that's going to give you is that one. Right, this one is going to give us that's going to give us magnesium hydroxide solid and barium sulfate solid. They're both solid, so that's going to give us more than the top one, and they react in a 1-to-1 ratio here. Barium hydroxide and sodium chloride, there's no solid. There's no barium chloride and sodium hydroxide are both soluble, no solid at all for that one. That's easy. And then this one again, you're going to get sodium hydroxide, that is soluble, and you're going to get barium sulfate. But in B, you're going to get you're going to get the magnesium hydroxide there as well. So B is the correct answer there. So that's all about group 2 solubilities, really, that question. 2. Indicator using the titration to find the concentration of methylamine. Now, methylamine is going to be a weak base. So if you just sketch that titration curve, you're going to get something like a hydrochloric acid. I'm going to draw it the other way around. I'm going to start off with the acid and add the methylamine. You're going to get a curve something like that shape. Right, so you want an indicator which changes. Right, thymol blue should be all right because that's changing down there. 1 to 2. Bromophenol blue would be better, I think, because that's going to be changing up here somewhere. Thymol blue could, yeah, so this is going to be the best one. Phenol red wouldn't be ideal because it doesn't change until it becomes quite alkaline, okay? And phenolphthalein would definitely be no good because that wouldn't change color till it's way up here when you've gone past the end point. So the best bet there is bromophenol blue. This one is a bit too acidic, okay? Maybe down in this region there, okay? Right, so this is Bourne Harbour, right? Bourne Harbour, or perfect, using calculations using the perfect ionic model. So when you get a difference, it's due to the ion shapes. The ion shapes are the positive. The positive ion distorts the negative ion. Okay, so which kind of positive ions are best at distorting? You want small, highly charged positive ions to polarize. So you've got a great big, cesium is bottom group 1, so that's really big 1 plus. Lithium is the smallest one in group 1, that's going to be the highest charge density. So it's got to be one of the lithium ones. Okay, now which one is it going to be, the fluoride or the iodide? Well, what kind of ions are easiest to polarize? It's big negative ions. Okay, so you've got a big iodide ion. Lithium is going to manage to drag some of that charge across like that. Now, why can't it do the why can't it distort the shape of the fluoride so well? Is because the nucleus of the fluoride is a lot closer to the electrons here, and so and there's not much shielding, so the lithium can't drag it over as well. Whereas the iodine, these electrons here are a long way from the iodine nucleus. There's a lot of shielding, so the large negative ions are relatively easy to polarize. So lithium iodide is the right answer. That would have the biggest distortion of the negative ions, or if you like, the most covalent character. So you get the poorest agreement between the theoretical and the Bourne Harbour values. Right, in equilibrium one, this is okay, almost a GCSE question. This, which combination of temperature and pressure would give the greatest equilibrium yield of products? Right, so we've got 2 moles of gas going to 3 moles, so we want low pressure. So it's either C or D. It's endothermic, so if you want to push it that way, you want to raise the temperature, you want high temperature, and then it will try and, let's just tell you, it will try and increase the temperature by going, decrease the temperature by going in the endo direction. So you want a low temperature, so D is the right answer there. Right, now I think that is the last question. Yes, it is. So that's the end of that paper.